Yeah, I have not tried it out. Maybe I will attach it as a extra slide with this PPT when I upload it. Okay, so I'll try to do it in either MATLAB or Python, and then maybe I'll try to upload it as a solution. Okay, in this PowerPoint presentation also. Whenever I upload. Okay. So today we will be mainly yeah, I'm recording. Okay. Today we will be mainly looking through basics of interface capturing methods for application in multi-phase flows. Okay. So this is mainly the week 10 content which I'll be discussing today. So I am Sumant Murul. I am a PhD research scholar in Department of Mechanical Engineering at IIT Bombay. So this is the tutorials for week 10 and this is session number 1, that is the Friday session. Okay, so I'll try to discuss some of the problems which are similar to your assignment problems. Some of the problems I'll try to discuss and some other problems will be discussed on Sunday's tutorial class. Okay, so mainly this week we have looked at mainly multi-phase flows. First of all, we saw what were multi-phase flows. What all kind of physics are mainly covered in multi-phase flows. So basically, in multi-phase flows, as the name itself indicates, there are two different phases, or there might be two different materials of the same phase also. So in multi-phase, you have two separate things. Okay, you have one is you have, say for example, say liquid or gas mixture or whatever it is. Okay, you have same phase but two different liquids or two different, let me write it as materials. Okay, then you have, in the second part, you have two different phases, like for example you have liquid and gas as a combination. Okay, or else you have a liquid and a solid also, although this liquid and solid is actually a different field altogether. It is mainly called as fluid structure interaction, and I mainly in my PhD thesis work on this fluid solid interaction mainly. But this is not mostly covered in multiphase, although technically we can say that this is multiphase. This is also multiphase. Okay. Okay, Divyendo, what did you find completed compared to earlier contents? Are you asking about this multi-phase this thing only, or are you asking about something else? Such a complicated. Yeah, maybe I will suggest some references at the end of this slide and attach it. Okay, so maybe you can go through some of the manuals for OpenFOAM. OpenFOAM is an open source software and it has multi-phase capabilities, and actually they have written beautiful documentation regarding multi-phase flows. I mean, which are mostly with respect to mathematical modeling of multi-phase flows, like what are the different types of methods which are there in multi-phase flows and all. So, okay, yeah, so maybe I'll send a link to that particular manual. Okay, so for the multi-phase flows, can maybe go through that because I also kind of had gone through that earlier itself some time ago. So maybe I thought that the things will become quite clear. Especially, they have actually kind of given the exact equations which are being solved in different methods, so that you don't kind of get confused between different methods which are there. Okay, but actually this week's content which I mainly saw, it is not about solving the multiphase equations. It is mostly on capturing the interface. You have to come up with a efficient technique to capture the interface. Okay, so that is the main idea behind this week's content. Okay. Okay, so let us continue. So what we were discussing is that in multiphase we have either two different materials, like you have a combination of say an oil and water mixture, okay, of the same phase of the liquid itself. You have two different materials, or else you can have completely two different phases like liquid and gas, liquid and solid, okay. So you have to kind of predict the accurate physics which will occur, okay, which you can see in the realistic situations also. So that is the main thing which you have to look at here, okay. So when you see two different phases, say for example liquid and gas, you can have one phase which is very continuous and other phase which is very discrete, okay. So for example, if you take some moment of say RBCs, okay, in bloodstream. So that is actually like a flexible solid in a liquid, okay. So this is not actually liquid and gas. This is kind of solid and fluid, you can say. So this is also a kind of multi-phase flows only. Okay, you have these RBCs, the red blood cells, which are kind of spread out in all the parts of the artery, all the vessels, okay. And it's not a very continuous phase. There is a break, okay, which exists. But whereas if you see the blood, it is very continuous in nature. So there is no break of blood stream which is happening, okay. So this is mainly called as the continuous phase, okay. Whereas these RBCs, the red blood cells, these are called as the discrete phase, okay. They are discrete phase. Now similarly, if you consider just water flowing in a river, which is a free flow of water, free shear flow. So you have just a water bed at the bottom, say, and then this water phase is in contact with the air, okay. So air is also continuous in nature, so that there is no breakage of air particles, and the water is also flowing, I mean, in a continuous manner. So there are no something like bubbles which are formed, okay. So these things are not there. So this is just simple flow of water. Say you can say it is flowing at a very low velocity, okay. So in this type of situation, this water is also in a continuous phase, and then the air is also in a continuous phase, okay. So this is a second category of multi-phase flows. Basically you have continuous phase and continuous discrete phase. Why we have to study, I mean why we have to know this is that whenever we come up with a solution strategy, we have to understand the physics which is happening before actually developing a strategy, okay. So for these set of problems, especially the continuous phase problem, maybe you will find out that one particular type of method, for example volume of fluid, may be a better method to solve. Whereas if you see the discrete continuous phase, uh, you can see that there might be some other methods, like for example Euler methods, which we will discuss later. So those might be better to solve such kind of problems. So that is why you need to understand the physics which is happening, okay. So that is why we kind of discussed this in the beginning. And coming to the application, so you can see for example in this particular example only of the discrete continuous phase, that we are trying to predict the physics of this motion of red blood cells, which is very important. So for example, we want to say extract only RBC particles from blood, okay, to do some testing, or say to transfer it to some other blood stream and just to purify this blood, or some requirement is there wherein we have to infuse only red blood cells in a particular patient. We need not infuse say this plasma, okay. It is not required. We need to infuse only red blood cells. In those situations, we have to be able to kind of extract these RBCs only. Okay, so you want to come up with such a design, okay, wherein the RBCs kind of get collected at one particular location, okay, and then there is a layer, or in there is a location where you have only RBCs and other location you have only plasma, so that you can separate out them very easily. So for example, if you take this converging type of section, you will find out that when we do simulations with using this multiphase model for this blood and consisting of RBC, plasma and RBC to be more accurate, what happens is that due to the shear force, uh, we usually see that there is a RBC free layer which is being formed near the wall. I mean, this is there in the literature. I am just trying to explain the application. Okay. So, and then you have the red blood cells which are coming more towards the center of the domain. Okay. And then maybe you can have a small nozzle kind of thing from which you can extract these RBC particles. Okay. So in this way, you will be able to extract only RBC particles and you will be able to separate out the plasma region. Okay. So this is an application, a real world application. So in this real world application, job of a CFD engineer or a job of a CFD scientist is to mainly see which geometry will assist this. Okay, so that is our main job. We have to come up with an efficient geometry and efficient flow conditions. So at the inlet you can have a pulsatile flow or you can have a steady flow. Okay, there are many combinations which are possible. You can have a parabolic velocity at the inlet, you can have a very flat profile of the inlet. Okay, in flow itself you kind of get these many combinations. That is one thing. Okay, second thing is the geometry, whether you need to have a converging and then diverging. Okay, or else do you need to have only converging and then a straight geometry. Okay, and then do you need to again have some nozzle, or do you need to have this a curved geometry or something like that. So there are again multiple possibilities here. So in those situations we have to perform multi-phase simulations. Okay, multi-phase study in different possible configurations, and then see in which of the configuration you get an efficient separation of red blood cell particles. Okay, so that is the main job of a CFD scientist or an engineer, okay, to study these things. So that is why we need multi-phase flows. That is why we need to study multi-phase flows. Okay, so this I was trying to just give an appreciation for this particular field. Okay, there are many other examples. For example, if you consider in aerospace industries, okay, so you have something called as sloshing of a tank, okay, which finds a great importance. So usually whenever you have a aircraft, so you have in the this is for example the wings. Under the wings there are some locations wherein you can store the missiles, or else you can also store a drop tank. Okay, a drop tank mainly consists of fuel inside it. It is used for two purposes. Mainly, first purpose, uh, what it does is that whenever this aircraft runs out of fuel, maybe you can supply the fuel from this drop tank only, or else the main purpose is to actually drop it at some specific locations. If you are running short of these ammunitions, other ammunitions, it itself can act as an exploder. Okay, so that is also, it is basically used an ammunition also in some certain emergency cases. Okay, so when you drop this, basically it's called as drop tank, that for that particular reason only. Okay, so when you drop this, it has to come and fall at one particular location only on the land. Okay, so in when it is falling, it has partially filled fuel, say. So what happens is that due to this fluid structure interaction, it is actually uh, computational multi-fluid structure interaction, because you have air, you have water, and then you have a structure also surrounding it. Okay, so due to the wobbling motion, what might happen is that it might change the force which is acting on the structure, and it might lead to this drop tank being uh, fallen on a different place altogether. So we need to ensure that the geometry is very kind of rigid in a way that it does not get influenced by the forces which are acting due to the wobbling motion of fuel inside this top tank. Okay, so that is another application. That is the application number two, which you find in the aerospace field. The first one I gave in from biomedical field. Okay, so I hope that there is a good appreciation for this particular topic. In this week, as I told earlier also, we mainly deal with only interface capturing methods and not actually, solving the multiphase equations and all those things. Okay, that is a different set of study altogether. So we mainly looked at the interface capturing methods. Okay, so mainly the first thing which you saw in this particular study, I would say, is that you saw uh, before going to interface capturing methods, you saw how the equations can be solved now. Okay, so basically you have two different fluids, or say you have multiple fluids. Okay, so one thing is that you can actually try to look at them as different fluids and try to solve them differently. Okay, that is different governing equations, I mean. And this we usually do in fluid structure interaction because the physics itself is different for fluid and say solid, although they can be unified in some special cases. But usually when we deal with fluid structure interaction, we have the Navier-Stokes equation, which we usually solve for the fluid flow governing equations. Okay, then we have the equilibrium equations, which are again the momentum conservations only. Usually they are called as the Cauchy stress equation. They are usually solved for the solid. Okay, so there are some slight differences in the governing equation. So basically we solve them separately and then couple through some interface conditions, which in multiphase is mainly called as jump conditions. Okay, so we have, like, this is mainly called as a multi-fluid approach. Okay, then you have something called one fluid approach to solve the multiphase equations. What you do is that, say I have water and an oil in this particular tank, or say water and air also. Okay, so I consider this whole body as only one fluid only. Okay, and then what I tell is that after you cross this interface, I will just change the material parameters. I'll be solving the same Navier-Stokes equation only. And this is in particular very helpful, I would say, when you are trying to especially solve the liquid equations. I mean, when you have liquid in your study. Okay, so in those conditions, doing such kind of studies will be really helpful, and it will reduce a lot of computational time also. Okay, you are solving only one set of governing equations in this one fluid approach. Okay, but you have to, one thing is, see, when you cross this interface, you will tell that I'm taking the, okay, whatever different material properties are coming, I'm taking that into account. But also you need to take into account this interface also. Okay, there are some forces which act on this interface. Okay, and the reaction force is built by the fluid, the other fluid which is there. Okay, so this is usually the surface tension force which comes into picture. Okay, so these are taken into account using the source term in the momentum equation. So that is what is usually done. So you have to take two things into account. One thing is the say the difference in the material properties, and then this force term on the interface. Okay, so that you have to take into account in the governing equation itself. So that is how you come up with a one fluid approach. In our multi-fluid approach, like for example, the way in which I told for this fluid structure interaction, what happens there is that, say for example, I have a flexible artery and blood is flowing inside this. Okay, now what happens is that this blood kind of imparts some force on this structure. Okay, so this is the interface between the blood and the artery. Okay, So whenever we try to solve this fluid structure interaction problem, whatever forces are applied by the blood are taken as the boundary condition for the artery. Okay. So whenever you solve for structure, you need some boundary conditions, right? So you need to know the stresses which are like particularly acting, okay, on the body, on this artery. So this stress is taken as mainly coming from, so stress on the solid is taken as the stress which is coming from the fluid. Okay, fluid kind of imparts some stress on the artery wall. Okay, so this you can take from the hydrodynamic parameters which you have calculated, the pressure plus mu into your again the shear stress tensor, dou u by dou x plus dou v by dou y. For just for 2D I am telling this. Okay, so in this way you can calculate the value of the stress which is acting on this solid surface and then model the solid surface. Okay, then you will get the deformations. This solid structure will deform to some extent, and that will be accounted by changing the blood flow domain. Okay, itself. The blood flow domain now it might become curved in a nature because the artery has expanded. So usually these things are done in fluid structure interaction. But as I said, in one fluid approach, in order to do these things are included as a source term only. Okay. So mainly there you will have surface tension force instead of this pressure force which is coming into picture for this fluid structure interaction. So that is the main kind of difference which you observe. So I have just tried to give some analogy between the various multiphase modeling approaches. Okay. Okay, so there is a question here. For two fluids, treating them as a single fluid with different properties can be considered. How can solid be treated as a fluid in case of solid fluid mixing? Yeah, we can try to adjust the equations in such a way that both of them become the same. Okay, so this is particularly if you see in fluid structure interaction methods, you have something like a monolithic approach to solve the FSI problems. There exactly people try to do the same thing. Especially what you told, that scenario is accounted in such cases. So for example, if we have a cavity and then if we have some small solid particles which are deformable in nature, and say there is some internal fluid flow which is happening and we want to try to solve for this structure also, this solid is actually kind of it is a solid only, but the equations are adjusted so that they become equations similar to fluid. Okay, uh, and say for example the elasticity uh, divided by 1 minus the Poisson's ratio, this particular parameter is considered as mu. Okay, just like how you have viscosity for fluid. So in this way equations are modified and then they are tried to solve in a single approach only. Okay, but this approach is not very helpful in such cases which I discussed here. Okay, wherein you have blood flow inside an artery. Okay, so there you have to model them mostly as separate domains only. Okay, but here you can have some viscoelastic solids whose governing equation itself is quite similar to fluid. Okay, in those situations you can try to do that. Okay, I hope I have answered that question. Okay, so now you have learned like what we are doing, like the equations which we try to solve, okay, for a multiphase flows. Now the main thing which I left out here was that although I told that we use only one single set of governing equations and implement the momentum source term to capture to consider the effect of interface, the important question remains, how do I capture this interface? Okay, so that is the main question which has to be asked, and this week 10 contents mainly goes on to discuss how do you capture this interface. Okay, so there are many methods which kind of exist. A simple method is to kind of come up with a function form to kind of say where the interface is. So basically if I have an interface something like this tank, so I will just write an equation for this curve. Okay, so as to define where the interface is. So that is one approach, and this is a very bad approach. Why you have discussed in the class also. Mainly you will get say for example two different y points, okay, for the same y, two different x points you will get, x1 and x2 you will get for the same y. In the class material it was the opposite way, okay. So this approach will terribly fail in many of the cases, okay. This is called as the I think the height function approach or something like that. So this was approach number one. Okay, then you have approach number two, which I would say as using the heaviside functions. Okay, so where you will mainly what you will do is that, okay, if I have, say for example, two different faces, I will identify them with as 1 and 2, or it's like for example 0 and 1, and then I will try to say uh, at this interface, so mainly we are getting grids, okay. So there is a combination of 0 and 1, so then I'll try to do some interpolation, and then I'll try to solve that, okay. But these are usually subject to some instabilities, because you can see that there is a direct jump which is happening from 0 to 1. So usually we go with a kind of diffused approach, okay, wherein there is a slow transition, and at this interface we usually have a fixed value of the interface, like fixed value of the function to be 0, which is usually called as level set method. This is a third approach to capture the interface, okay. And then you have here it slowly goes away from 0, okay, and in the other phase also it goes slowly away in the opposite direction, okay. It goes slowly away, it is not just a direct jump which was happening like in the heavy side approach, okay. So that is the difference between this approach number 2 and 3, that is level set and this heavy side function approach, okay. So these are mainly the three approaches to capture the interface, and then finally to solve the multiphase flow, like after you capture the interface and all, okay. So then you have different methods like volume of fluid, and then you have something like Euler approach also. As I said earlier, maybe I will share some documents regarding this. You can also go through those documents apart from your say class materials, okay. So that will help you to gain a better understanding of the methods, okay, to solve the multiphase equations. And that is out of syllabus. I mean, this content was mainly focused to learn methods to capture the interface, but if you want to really solve the multiphase equations itself, you can go through those things if you are interested, okay. With this, let us try to see some of the problems for this week content, okay. So this is what I was discussing till now, okay. This was just a brief recap which I gave, okay. Sorry. So in the question number 1, we have continuous phase interaction is observed in which of the following situations, okay. So what should be the probable answer for this question? Can you write on the chat box? Okay, so let us try to see them one by one. So first you have a slurry flow through a pipe, okay. So basically it's like a mixture of water and say cement or some clay particles or sand, something like that, okay. So that is usually called as a slurry, and you usually find like these examples you come across during the in the metallurgy field, okay. You kind of have this slurry which is say flowing inside the pipe, and what might happen is that due to a very high speed of slurry, this might kind of break down into smaller particles which have been indicated in circles here, and these usually form a discrete phase. This is not dispersed, this is discrete phase, okay. And then you have a fluid like water for example as a continuous phase, okay. So you have a continuous and a discrete phase in this case, so it is not a continuous phase, okay. So if we come to the second example, it is the free surface flow of water in a river. This example just now I explained it while giving the brief recap of the weekly contents also. that we have both air and water as a continuous phase. Okay, so because there is no discontinuity or there is no breakage of water molecules, okay, as a different particles, they all exist in one particular, you can say, you can mark a volume, particular volume, and say at a given time instant, within that closed volume itself, the water and the air particles are there. So that is why it is a continuous. Okay, yeah, both of them actually mean the same. I mean the dispersed phase and the say the discrete phase also. Okay, so usually the terminology is used in an interchangeable manner. Okay, so that is why I think I had indicated dispersed phase also, but in the questions you have it as a discrete phase also. Okay, so both of them you can consider it to be same. So here I have used the discrete phase as a terminology. Okay, both the terminologies have a same meaning. Okay, so that is why I have indicated the both the terminologies here. Okay, then you have option number C. You have a cavitating flow around a rotating propeller. So basically, what this cavitation means is that basically you initially have only one fluid, okay, which is coming in contact with say air or something like that, and then due to some external forces which act on the fluid, which might be due to a converging nozzle, or in this case due to a rotating propeller. Okay, due to the kind of geometry or due to the kind of external forces, it kinds of breaks up into small bubbles. Okay, these are small bubbles which it breaks into. Okay, um, it would not be, it would not be accurate to say bubble. It would be more accurate to say droplets, I think. Okay, so it kind of breaks into the small water particles, okay, which here I have indicated as a discrete phase. Okay, and then you have the air which is a continuous phase. Okay, so that is why again this is an example of discrete continuous phase, and it is not a continuous phase. So I think the next option is the sand falling through a hopper. In this also it is a similar case. You have these fine sand particles which kind of come out from their main the falling region, and they exist as a discrete phase. Okay, and here you have it as a continuous phase. So this is also a continuous discrete phase example. Okay, so you have only one option which is correct, that is the free surface flow of water in a river. Okay, so that is the option number B. Yeah, you are correct. Okay, so let us see the next question. I think it is the opposite. Okay, so discrete continuous phase interaction is observed in which of the following cases? Okay, flow of bubble laden liquid in a pipe, or sprays, or clouds, or none of the above. So what do you think should be the correct option for this question? Can you write down on the chat box? B and C. Okay, let us try to see with A first. Okay, so you have flow of bubbles in a pipe. Okay, so you have in a pipe, you basically have water which is flowing initially here. Okay, because there is some fluid which is flowing, and in between you have bubble also. So basically bubble means it basically has gas inside it. Okay, you can say it has some air inside it. Okay, so it is a different phase again, right, but it is spread out at different points in the domain. Okay, so it is a discrete phase, it exists as a discrete phase, the bubble, whereas the water which is there, okay, it is in a continuous phase in this pipe. Okay, so bubble laden liquid in a pipe, so that is an example again for this discrete continuous phase. Okay, so that is why option number A will also be correct. Okay, so I hope you have understood why. Okay, because we have a bubble which has gas inside, entrapped inside it. Okay, and then sprays, you all know that when it comes out of the enclosed space, it kinds of expands into the air, and then a small kind of droplets are formed. Okay, not bubbles. I would say droplets. Small droplets are formed. That is an exist in a discrete phase. Okay, and then the air you have it in a continuous phase. So this also is an example for discrete continuous phase. And then clouds also in a similar fashion. You have the water molecules accumulated to form clouds which are at different positions. Okay, and so that is the cloud itself is a discrete phase. Okay, and then you have the air which is in a continuous phase. Okay, so this is an example of again discrete continuous phase. So all the options are correct actually, A, B and C. Okay. I hope that this is understood. Okay. So now if we see question number 3, it is about the one fluid approach which we just discussed in the recap of the session. Okay. If one fluid approach is applied to a two-phase problem, the following assumptions, actually it should be which of the following assumptions are valid. Okay, these are valid. Okay, so as we have discussed just now about this one fluid approach, can you write down in the chat box which of the following has to be the correct option? So the first option is interaction terms model the exchange of mass, momentum and energy between the two phases. Okay, so some terms are added, they are saying, which can model the exchange of mass, momentum and energy between the two phases. Or else the second option is various phases are treated as one fluid with variable material properties. Okay, the third option is appropriate jump conditions are used to couple the equations across the interface. So mainly I told you this earlier also, that by giving an analogy with fluid structure interaction, that whenever we try to solve the physics by using two different governing set of equations, we usually have the interface coupling which happens, which we need to apply. So there we have like interface condition in fluid structure interaction, where we have stress continuity, wherein the stress which is enforced by the fluid is being applied on the structure as a boundary condition. So that is the interface condition. In multiphase flow, we have something like jump conditions. Similarly, it is a similar term. Okay, this jump condition. So we have to ensure that some properties are satisfied. So for example, one is the velocity continuity, which comes in due to the jump conditions. Okay, which we have to satisfy, and this we have to satisfy only when we are solving two different set of governing equations, which we don't do in one fluid approach. Okay, so you are telling all are valid. So the thing is, as I said just now, okay, these jump conditions, or else let me tell in FSI words, it is the interface conditions. They are needed, okay, only when you are trying to solve two different set of governing equations. Okay, the different physics when you are trying to solve, like for fluid and for structure. And then at one point you have to say couple. You have to make sure that some conditions are correct. But here we are trying to solve only one set of governing equations, right? So we need not enforce these jump conditions. Okay. What happens is that these kind of conditions are inherently being satisfied by adding some source term in the momentum equation itself. That is the option number 4 actually. The interface is introduced as a singular distribution. Okay, so because you don't have a like for say different variable for say the phase 1 velocity, phase 2 velocity, you don't have separate variables in this one fluid approach. You have only velocity. Okay, then how will you apply the jump condition? Jump condition means velocity of this phase is equal to velocity of the other phase. That is one jump condition. So that you cannot just apply it in this one fluid approach. Okay, because you are treating it as a one fluid only. Okay, so what you do is that one thing is, as I told in the recap also, various phases are treated as one fluid, okay, with variable material properties. So that is why I had discussed, okay. You kind of take different material properties across the interface and then try to solve it using only one set of governing equation, one set of mass, momentum and energy equations, okay. So option number B is correct. And then you do not do this option number C, like do apply the jump conditions, okay. So option number C is incorrect. If you see option number D, that is what is being done in one fluid approach to treat the interface, okay. So you add some extra terms, okay, which can like enforce a continuity of say surface tension for this multi-phase flows, okay. So option number D is also correct. And we do not have any interaction terms which model the exchange of mass, momentum and energy, okay. Because we are treating them as one phase only, there is no concept of two phases, okay. So that is why option A is also incorrect. So you have only B and D which are the correct options, okay. So that I have tried to uh, explain it using a simple our incompressible Navier-Stokes equation. So for whole domain you are solving this particular equation only, okay. You can see that till here it is our same previous Navier-Stokes equation which we had discussed, okay, in the previous weeks. It's the same thing. Extra you have only one particular forcing term, okay. This is a body force term with singular distribution to account for the interface, okay. So basically the stress continuity, the jump conditions are basically enforced using this particular term, okay. So that is the main difference which is happening, okay. Am I audible now? Sorry, am I audible now? Can you write on the chat box? Okay, I think there was some issue. Okay, just let me keep this off. So B and D, both of the options should be correct for this question. Okay. So the continuation of this question is question number 4, wherein in one fluid approach the surface tension is included. So as I told earlier, that this F bar term, which is added as a source term, it incorporates the kind of continuity in the surface tension. Okay. So that is why the option number D should be correct. Option number A, you have jump condition across the phase interface. So that is done in multi-fluid approach. That is not done in one fluid approach. And heaviside function across phase interface. Okay, so you don't do that to include the surface tension. That is done to include the material properties. Okay, to change the material properties, you are using the heaviside functions. Okay, and then so that is not done to include the surface tension, okay. Surface tension will come only at the interface, okay, whereas this heaviside function is mainly used during the calculation of the properties and all, okay. So that is not a correct option. B is not a correct option, okay. Source term in the continuity equation, no, we do not enforce source term in the continuity equation, it remains same. We enforce source term only in the momentum equation. So for this only option number D should be the correct answer, okay. I hope that this is understood, okay. Now let us go to the next question, which is again based on whatever discussions we have done, okay. The height function h equal to it should actually be, I think, okay, h of x comma y, okay, it should actually be y is equal to h of x comma some time, okay. uh, and we are particularly seeing this at one particular time, okay. We are trying to kind of calculate the value of y, okay. Okay, in this previous question you are not here why b is not the correct answer, okay. See, in the question they have asked the surface tension is included as, okay, surface tension is included as a source term only in the momentum equation. The heaviside functions across the phase interface, they are not required, like see, across the face interface, you need not satisfy the jump conditions, right? First of all, the heavy side functions, they are mainly used to kind of calculate uh, the velocity. Okay, so for example, you have this particular u term, right? So you need to find which u is this. Okay, so although we represent it as only one variable, so you can use the heaviside function and say 0 into u1 plus 1 into u2. That is in the internal domain, far from the interface. Okay, so there you are. Okay, am I audible now? Am I audible now? I think there is some connection issue which is happening. Am I audible now? Okay, okay, thank you. I think there is some connection issue which is happening. Okay. What I was telling is that, see, you need to calculate this u, right, in the regions apart from the interface also. So there you kind of use the heaviside functions to calculate the value of u. So you take it as u is equal to 0 of u1 plus 1 into u2, because you have only phase 2 in that particular region. So there you are using it, but this surface tension, okay, so that is being included as a body force term only in the momentum equation, as a source term in the momentum equation. This is used for a different purpose. Mainly you can say that it is used as an interpolation kind of function, okay, to calculate the value of variables. Okay, so for surface tension that is not required. Say you can say that it is required for this u. Okay, and say p also. Okay, and say you can say the mu viscosity, effective viscosity. Okay, so there you can use these functions, but the question asks about surface tension, so there these things are not used. Okay, only the option number D should be correct. Okay, I hope that that is understood. Okay, is that clear? Okay, so okay, thanks. Question number 5. It was asked about the height function. This is actually not spelled correctly. I think it should be y is equal to h of x comma t. Okay. So we want to find out the value of y using a height function h. So we have a closed interface denoted by s. So do you think that we can use this function, the height function, to kind of track this interface? I mean, we can use it, but as I discussed in the recap also, you will get two values of y only for one singular x value. Okay, so this will create ambiguity when you are solving. Okay, so you will not understand where you are while solving these governing equations if you use this height function. Okay, so you cannot use it. So you cannot use it to track the interface. So false should be the correct answer. Okay, in question number 6, in this weekly contents, mostly the questions are on a theoretical side, at least in the first session, that is on my side. Okay, maybe in the second session you will get some questions which are a little bit of numerical. Okay, but mainly this weekly content is mainly aimed to uh, get an understanding of interface capturing methods. Okay, whereas if you see in the previous classes, the objective there was that you have to solve some equations and try to get the physics. Okay, but here that is not the objective. That is what I have understood. Okay, I might be wrong also, but mainly here it is being addressed so that you understand how to effectively capture the interface. Okay, so that is the main thing. Okay, so a method using marker function is known as which of the following? Okay, advancing front technique, front tracking technique, front capturing technique, and moving front technique. Okay, so this marker function, as I told earlier, so what we do is that we have a sharp interface, okay, in realistic situations, but we try to smoothen it out, okay. So and then we use a function, say phi, okay, which we equate to 0 on this interface, and then we try to say in our domain where this phi becomes 0. So that is what we are trying to do. We are just trying to capture the interface, okay. We are not trying to exactly pinpoint the x and y values, okay. So in a computational setup you can understand it like this, okay. uh, Say I have come at one particular point and I just want to know whether there is an interface or not at this particular grid point, okay. In this above grid point there is no interface, below grid point there is no interface, okay. I have just come to a grid point, okay. Irrespective of the location I want to just know whether there is a location, there is an interface or not. So you just want to capture the interface here. You do not want to track the interface. Tracking means you are kind of locating the xy values and all those things, okay. So that is particularly tracking. So here it is just to capture it, okay. So when you come to the this below grid point you will see that the phi value goes below 0. Above, if you go, if the phi values goes above 0, and only at this grid point you somewhere have phi is equal to 0 which is coming up. So you are say you are capturing the interface. I am just capturing the interface, so that is what is being told, okay. So that is why in this particular question I think the option number C should be correct answer, okay, not the front tracking method, okay. And then we have I think this is the last question, phase interface definition based on iso contours. So this is again related to what we just discussed just now. The level set method which we discussed just now kind of smoothens out the interface, okay. Like we have, it doesn't smoothens out the interface actually, it kind of helps us to identify the interface smoothly, okay, instead of a sudden jump which we have, okay. So that is why the level set function is used, and usually we have the iso contours of phi is equal to 0. The what is meant by iso contour is that along this whole interface you have single value of phi, okay. Along this whole beside region I would say you have a particular fixed value of phi which is less than 0. Above that again you have a fixed value of phi. So at this particular distance, okay, d1 I will call it as, whatever comes d1 here also, so there also you have a fixed value of phi which is greater than 0, say 0.1, okay. Phi is equal to 0.1. Here it is phi is equal to minus 0.1 along this line, okay, along this whole line. So that is why it is called as an iso contour approach, okay. And that is why for this question option number D should be correct, but let us also try to look at the other options also, okay. Height function is actually a mathematical representation, okay. There is no contours or something, it is just a mathematical representation to calculate the exact location of the interface, okay. And then in volume of fluid you kind of use volume fraction, you do not use this iso contour approach, you just use some volume fraction to track the interface, okay. Say for example at a particular grid point, again let me go to this particular example only. What we do is that we have this three grid points, so volume fraction of gas I will say phi will be equal to 1 in this particular case, and at the interface grid phi will be 0.5, say equal amount of I have water and air, then phi will be equal to 0 when we wherever we have pure water, okay. Volume fraction of air is 0, whereas in this outer side the volume fraction of air is 1, whereas at the interface we have volume fraction of both. So volume fraction of air, say it will be 0.5. So through this method we are trying to kind of capture the interface in that volume of fluid method, okay. We are not using an iso contour type of stuffs here, okay. So that is why that is also an incorrect option. Cubic interpolation, pseudo particle method. Okay, so here you have CIP scheme, which is basically again kind of mathematical representation but using a cubical curve. So again it's a mathematical representation, and that is why it's not a correct option. And then you finally have the level set method, which I explained it. Okay, so you will get a constant value of f, okay, along that particular line, which we call it as contour here, okay, for 2D. So that's why option D, that's the last option, should be correct. Okay, the last question is slightly on a mathematical side. Okay, so you have this particular, I think the image is not full here. Let me just. Okay, an infinitesimally thin phase interface S, this is S. It is separating two incompressible viscous fluids. Okay, and the normal is given by n cap, and the interface is moving with a velocity v, whose normal component again is vn. Okay, v dot n is vn. Okay, okay, the interface, the phase 1 has a velocity of u1 and phase 2 has a velocity of u2 near this interface. Okay, and they have density rho 1 and rho 2. What are the jump conditions, suitable jump conditions they have asked in the question? Okay, can you guess the answer for this? Yeah, so we mainly have mainly the mass continuity, mass flux in is equal to mass flux out of that particular interface, and since we have an incompressible flow, that will be zero. Okay, so mass flux you can express it as um, rho into velocity, right? So rho into effective velocity here, because the interface is moving, so that is why you need to consider uh, u1 dot n, that is along the interface, minus vn, because the interface is also moving, right? So that is why you need to account for the interface moment also by this particular term, minus vn. Otherwise it would have been just rho 1 u1 dot n if the interface was not moving. Okay, similarly you have rho 2 into u2 minus 2 dot n minus vn. Okay, so since it is an incompressible flow, okay, this will be equal to 0. Okay, and what you can do next is that you can equate both of them to 0, and since rho 1 rho 2 they cannot be 0, so only left out thing is this u1 dot n cap minus vn, so that needs to be 0. That is the velocity, I would say effective velocity should be 0. That is the effective velocity, that should be 0, and that is why B is the correct option. Along with that, you can further simplify this also. Okay, first of all, B is correct option, and then what you can do is that, so this velocity of the fluid minus the velocity of the interface for phase 1 should be equal to phase 2. Okay, so if you do that, vn will get cancelled out, and since n cap is same at the interface, so you will finally land up with u1 vector equal to u2 vector. Okay, so option number D is also correct. Option number C, it says rho 1 into magnitude of u1, so that is why it is not correct. Okay, if you had only rho 1 into vector of u1, that would have been correct, but since they have given magnitude, option number C is not correct. Okay, so B and D both are correct. Okay, so these were the questions which I wanted to discuss today. So if you have any queries, you can ask now, or you can mail me also. Okay, so I'll try to attach the link for the open form manual also, and then I'll upload this. Okay, slide. Okay, simple algorithm, I was going through these things, so I have not got sufficient time to deal with it. I'll see, maybe next week if I get some time, I'll try to discuss it. Okay, so yeah.